Okay, so first we're going to look at how to eliminate the backgate effect. So the first thing that we do if we have a transistor, so here we have an Nmos transistor, and let's say that our bulk is tied to ground, like it almost always will be, then the easiest way to eliminate the backgate effect is, well, if that's the case, why don't we just always tie our source to ground also? Or why don't we just, in fact, instead of tying our bulk to ground, why don't we tie our bulk directly to our source voltage? So here we've tied the bulk directly to the source instead of tying the bulk to ground. But most often we're using a process called a bulk Cmos process. So in a bulk Cmos process, we make all of our N transistors in the same P- well. Okay, so here we have an Nmos transistor, and let's say over here we have another Nmos transistor. And next to these Nmos transistors, we usually put a P+ region. So here's our gate. Alright, so we know that we're going to try and tie this P-type material to ground, and the reason is we have these parasitic P-N junctions, and we'd like to make sure that the P region is always tied to ground so that we can't forward bias that junction, or at least it would be very difficult to forward bias that junction. So let's say that this is my drain of this transistor and this is my source, and I want to tie my source directly to the bulk connection, this P+ implant. Well, if I do that, because this P+ implant is at the same potential as this P+ implant, we're grounding the entire substrate, then that would mean that this transistor's source would be connected to ground no matter what I did. So I can't make that connection and still achieve, for instance, a common drain amplifier. So what can be done is add some cost to the process. So the first thing that we could do is they do make processes called triple well processes. And in a triple well process, I would be allowed to do something like so. So we start with the same P- material, but then I could make an N- material and another N- material, and then inside of this I could make another little P type region, and here I could put my MOS transistor, and in this case I could tie the bulk to whatever potential I'd like to tie it to, because it's isolated inside of another well. So here I have my Nmos transistors, and they're floating inside of their own wells, and in this case I can tie the well to whatever potential I want to tie it to. The problem with this is it costs a lot. And the reason is that I have to add a lot of mask layers to do this production. Not only do I need extra mask layers, but because I can't put these transistors very close together, it's larger in area as well. Because I have to have these two different wells isolating each other, so I can't move the transistors as close together in this particular process. We'll call this one L1, this one L2. So we would say that L L1 would be much greater than L2. So not only is it more expensive, but it's also larger, and that's a problem because larger circuits cost us more money also. So the modification that we're going to make to our small signal model is that, for instance, in our common source amplifier, we're going to say that Vs is equal to Vs over Vg, our gain, is equal to Gm times RT still, but in this case we're going to say that Gm is equal to little gm divided by 1 plus Gm plus GMB times our dollar sign. And of course our total is equal to our little d in parallel with our big D, just as it was before. So I'm going to make a formula sheet where you're going to prove these derivations. But in general, the only modification we have to make is that whenever the bulk to source voltage is not equal to 0, then GMB is not equal to 0 either, and you have to include it in the equation. So that will be in your second homework that will be assigned this coming Wednesday to prove these particular derivations. I'll post the formula sheet up on Canvas along with the lecture notes. Until next time.